Hi guys, welcome back to my YouTube channel. So today we'll be reviewing AP Statistics Unit 2. So first off, some definitions. Parameter. It's a numerical summary of a population. And then like an example is like the height of all MCSM students. A statistic is a numerical summary of a sample. An example is the average height of a random sample of 50 students from MCSM. And explanatory variables, also like you could think of it as like the X or the independent variable, predicts or explains trends in the response variable, which is also like you could think of it as a dependent variable, which is a variable getting measured. I like to think of it as the explanatory variable explains the response. So graphs used for quantitative data. Scatter plots, which visualize trends between two quantitative variables. As we see here, this is how a scatter plot looks. Both the values are quantitative, numbers. Unusual features are clusters or apparent outliers. This is what an unusual feature would look like. It doesn't follow the pattern. Forms are either linear or nonlinear. So look at the graph. It's either linear, no matter what type of other pattern it is, it's just nonlinear. The linear regression model. This is the linear regression model. Y hat, the sign over the Y is called hat. So Y hat is the predicted values of the Y. Basically, yeah, the predicted Y value. And then B represents the slope, the rate of change. X is the explanatory variable X. And A is the y-intercept. So, how do we describe a linear regression model? We use DUFs. D stands for direction. Is it in a positive direction, like going up, or is it in a negative, so going down? U for unusual features, so basically outliers or clusters that don't follow the pattern, like we saw in the other example. F for form, so linear or nonlinear. What's the form? And then S for strength. Is it strong? Is it moderate? Or is it weak? And also, we always need context. Yeah. So, correlation. This helps us to determine S for strength. So, the correlation coefficient. It gives us a direction and quantifies the strength of a linear relationship. As we see here, the correlation coefficient is from -1 to 1. -1 indicating that it's strong, very strong, but it's negative. That's why there's a negative sign. But if it's +1, it's very strong, but it's positive because it's positive value. But if it's 0, the closer it is to 0 is the weaker it is. 0 is a weak correlation. No, there is none correlation at 0. So, ways to describe a correlation in your or strength in your response, which is like perfect positive, which would be 1, a strong positive, moderately strong positive, weak positive, no apparent is 0, and then it goes all the way to perfect negative. A coefficient of determination, which is r squared. It's the percent of variation in the response variable that is explained by the explanatory variable. So basically the variation in the y, the predicted values. What is the variation of it that is explained by the explanatory variable? And it's from 0 to 1, which makes sense because -1 squared would be 1. You can't have a negative value and it'd be squared and still be negative. So closer to 1 is stronger and closer to 0 is weaker. So could we predict data if x was 3 meters? Technically, we could by inputting 3 into x, but it would be an extrapolation. Extrapolation is predictions made outside of the interval of our current data's x values. Current trends may not continue, so it's not really accurate. Residuals. Residuals are the difference between the actual response value and the model's predicted response value, which is the formula y, which is the actual value, minus the predicted value, y hat. So this is what it would be here. The point would be y, the actual value, and then where it is to the line is the predicted value. So if the residual is positive, that means the predicted value is less than the actual value, which makes sense because if we were to get a positive number, that means y hat has to be smaller than the actual value. And then if a residual is negative, that means the predicted value is greater than the actual value. So to produce a negative number, y has to be less than y hat. Like example, if y is 5 and y hat is 8, the residual will be negative 3. And that's an overestimate because y hat is actually bigger than what the actual value is. A residual plot good fit. It's random scattered and it's centered at 0 with no clear pattern. A residual plot bad fit if it has a pattern. So a residual plot shouldn't have a pattern. As we see here in the picture, if it's linear or like somewhat linear, the residual looks scattered everywhere. But when it has a pattern like a curved shape, the residual also shows a curved shape. Now, a least squares regression line. It's a linear model that minimizes the sum of the coefficient of determination, r squared. And it contains the point, the average of the x values, and the average of the y values. It contains that point. And also it contains the slope b to be r, the correlation coefficient, times the standard deviation of y over the standard deviation of x. So now for interpretations. To interpret the slope value, we usually use this format. For every 1 unit increase in the explanatory variable, our model predicts an increase or decrease of slope in our response variable. And for interpreting the y-intercept a, when explanatory variable is 0 units, our model predicts that the response variable would be the y-intercept value, the a value. And you don't have to use this exact format, but it should include the same information. Now, outliers. High leverage points are points with unusually large or small x values, so they're far away from the x value. Influential points are outliers with changes r, and high leverage points changes a and b. High leverage points may sound like outliers, but high leverage points are specifically those points that are super duper far away to the right or left, because it's the x value that's changing, not the y. If we added a point really much on the far right and left, a, b, and r all changes. If a point is added below or above, the b stays the same, while a and r changes. Honestly, I don't even have these rules specifically memorized. I just think, and then we add the outlier over here. Think of the outlier as a weight. So the line is going to shift down towards that weight. So it's going to look something like this. It's shifted down towards that weight because it's heavy. So now we know that the y-intercept increased and also the slope decreased. We know that because slope is rise over run. So the run is getting larger, and rise over run. If the denominator is getting larger, that means the number is becoming smaller.
Like and subscribe and comment.